Today's webinar is the fourth in our 5-part series on Eddy Covariance. Jiahong Li and James Catalonco will be your presenters today. Jiahong and James are both application scientists for LI-COR. Their talk today is titled The Eddy Covariance Method, In-Depth Theory and Data Processing. Jiahong will be opening for us. Jiahong?
Thank you, Ashley. Hello and welcome from LI-COR Biosciences here in Lincoln, Nebraska. It's so nice to see all of you joining us for the webinar. Today we'll discuss in-depth eddy covariance theory and data processing. In the previous webinars, we covered an introduction to the eddy covariance method, talked about system design and instrumentation, and introduced our new data processing software, Eddy Pro. The 3 previous webinars are available on our website. This webinar will give us an opportunity to further discuss data processing from a theoretical perspective. Some of you may be new to the eddy covariance method. If you have difficulty following any part of this webinar, please email us your questions and comments during or after this webinar. Just a reminder that we have a strong scientific Flux team here at LI-COR to share information and experience with you, as well as to support your eddy covariance measurements. Okay, let's begin our first webinar. I'm Jiahong Li. My colleague James Catalonco and I will be presenting this webinar. As I mentioned before, the main focus of this webinar is on data processing. James will discuss the source of error and how to implement different corrections. Before we get there, I will review some fundamental theories related to data processing, just so we'll have some background as we move forward. It looks like we have a large group of participants, so now I'm going to launch our first poll. This anonymous poll will allow you to evaluate yourself and see what level of eddy covariance experience this group has in general.
So let me open our first poll question. I'm going to walk you guys through since this is our first one. The question is, how much do you know about the eddy covariance method? And the choices are, I have only heard about eddy covariance and am not using it. I'm familiar with eddy covariance but am not using it. I know eddy covariance and am collecting data. I know eddy covariance and also collect and process data. And I consider myself an expert on the eddy covariance method. So just choose the radio button next to your answer choice, and we'll give everyone a few moments to finish.
The results is what we expected. Thank you for your participation. Airflows can be broadly classified as laminar and turbulence flows. In laminar flows, there's no mixing across different layers. By contrast, in turbulence flows, spatial and temporal transfer of flows and scale properties happen all the time. Let's take a closer look at the turbulence flow, since they are the most frequently encountered type in the atmosphere. Here we have 3 important characteristics of turbulence. First, turbulence flows are chaotic and mechanistically unpredictable. Therefore, we have to use statistics to deal with turbulence, which is also why we use covariance to estimate fluxes. Second, turbulence flows are 3-dimensional, so we need a 3-dimensional sonic anemometer to measure horizontal, lateral, and vertical wind speed. Third, all turbulence flows consist of multiple scales of eddies. For the atmospheric boundary layer, the typical range of eddy size is from millimeter to kilometers. Those eddies are cascaded, and the energy transfer occurs through their entire spectrum, That's why we need a high-speed instruments to catch the small eddies, and why we use a proper averaging period in data processing to account for the large eddies. To mathematically deal with turbulence, we treat each individual data as a means plus a deviation using Reynolds averaging rule, as you see here for sonic temperature. Here, all bars represent means, and prime stands for deviation. Reynolds averaging is a key statistical technique for dealing with turbulence flows. In our first webinar, we discussed the eddy flux formulas and how they are derived. You already knew that flux is equal to mean dry air density multiplied by the mean covariance of vertical wind speed and the gas mixing ratio. So we are not going to repeat what we already discussed, but rather focus on some important concepts related to data processing. Here we introduce the basic mathematical formula for vertical wind speed profile and the related terms such as friction velocity and zero displacement. For rough surfaces such as forests and crops with neutral stability, the vertical wind speed profile follows this equation. Here U of z is wind speed at high z, U star is friction velocity, and d is a zero-plane displacement. With this equation, we can determine the vertical wind speed profile over the surface. At this point, some of you may be wondering what neutral stability means. To understand the atmospheric stability, we need to first look at the morning observed length. Eddy transfer is determined by two forces, mechanical force and buoyancy. To better understand this, just imagine a hot air balloon. It moves from one place to another horizontally due to the mechanical force of wind, and moved up and down by buoyancy. The morning observed length describes the balance of those two forces. As you see here from the equation, the morning observed length is affected by virtual temperature, friction velocity, and the sensible heat flux. Now we can easily understand the atmospheric stability. If the ratio of Z to L is negative, the atmosphere is unstable. Unstable conditions usually occur during daytime. They enhance turbulence. When the ratio of Z to L is positive, the atmosphere is stable. This usually occurs at night and suppresses turbulence. Neutral stability occurs when air becomes infinite. This type of stability is the most common type. Knowing atmospheric stability is very important because many equations in the Eddy Covariance method vary with stability.
Jihong, I'm going to interrupt you with a question from the audience. I'm seeing a lot of equations and formulas. Do I need to implement all of these to get flux values? And if so, how?
Yes, to get your final correct flux results, you need to implement these equations. You can use computer program languages to develop your own codes, or you can use existing data processing software. There are a few available in the Eddy Covariance community. We have one available on our website. It's named Eddy Pro. In this webinar, we'll show a lot of equations, but don't worry about them. We just want to demonstrate the theories behind the data processing. Okay, let's get back to the discussion. We are going to look at the relationship between sonic virtual temperature and air temperature. By definition, the virtual temperature of moist air parcel is the temperature that dry air would have if its pressure and density were equal to those of the moist air. Based on the ideal gas law, we can derive the relationship between virtual temperature and the real air temperature. As you see here, the difference between virtual and the air temperatures is affected by water vapor partial pressure and air pressure. To do frequency correction, flux data needed to be transferred from a time domain to a frequency domain using Fourier data transfer. The basic principle is that any periodic data can be decomposed into a linear combination of sines and cosines. For example, the data on the top graph are the sum of all the sinusoids on the bottom graph. A good analogy is solar radiation. If we measure it with a pyranometer, we get one value. This value is a composition of different lights and different wavelengths. The math for Fourier data transfer is very complex, but we can do it using computer programming. Once the data are transferred from a time domain to a frequency domain, frequency correction can be carried out with spectral or co-spectral analysis. Here is an example of co-spectral analysis. Because both vertical wind speed and sonic temperature are measured by a sonic anemometer simultaneously, there is no sensor separation, time delay, and other frequency-related issue. So the frequency response of sensible heat flux is usually considered ideal. Compared with it or model, frequency correction for CO2, water, and methane can be achieved. Okay, it's a good time to do a poll question.
All right, it looks like Jiahong has the second poll question for you guys here. Why don't we go ahead and read through the question and take a look at the answers, and then I'll pop the answers up, or the poll up, so that you guys can click and answer. So the question is, which is the correct co-spectral response curve? Jiahong, would you like to talk through some of these responses?
Thank you, Ashley. Here we have some possible co-spectral response curves we could see from real measurements. Since you are not able to see this graph in the coming poll, please write down or remember your choice. I will explain the curves after the poll. Ashley, you may pop up the poll now.
Thanks, Jiahong. So here's the question, and just choose your answer, A, B, C, D, or E, and we'll give everyone a few moments to select.
Thank you, Ashley. Let's look at the answer to the poll question. I added the ideal co-spectrum to the graphs as indicated by the blue curves. Now we can easily see the correct answer is D, because the instruments are capable of adequately sampling turbulence exchange. A is not correct, because the instruments are too slow or they were placed too close to the canopy. For B, the instruments are too slow and noisy. For C, the instruments are not capable of measuring turbulence exchange, or the data were miscalculated. For E, the instruments have incorrect sampling frequency, resulting in signal aliases. I'm stopping here to let James continue the talk. Thank you.
Thank you, Jiahong. While James is taking his spot, I'd like to remind our audience that this webinar will be available on the web in a few days, and that you can also access any of the previous Eddy Covariance webinar recordings from our website at www.li-cor.com/env/webinars. James?
Thanks, Ashley. Hello, everyone. In this section, I will go through the different steps in Eddy Covariance data processing. We will look into the underlying equation and the basic theory. So let's begin with the data processing logic. Eddy Covariance data processing consists of a series of steps which has to be undertaken in a particular order to obtain the correct fluxes. Once you obtain the raw data, and you do the unit conversion, the data has to be hard flagged for quality control. This is followed by the coordinate rotation. The data from the gas analyzer and the sonic is then aligned and is detunted to obtain the mean and fluctuating part. This is followed by a series of corrections which involve correcting the WTV covariance, the frequency response or spectral corrections, and the WPL corrections to obtain the final flux. The flux data is then flagged for quality control. So the first step after you get the scalar concentration and wind velocity data in the right units is to flag the high frequency data for data quality. Data can be hard flagged for quality as 0 for good quality and 1 for bad quality. Although different kinds of hard flags are prescribed, I'm going to go through a few important ones which are implemented in the Eddy Pro software. 7 of the important hard flags are presented here. We will go through each of them in the following slides. The first hard flag is based on spike detection and removal. Spikes in the data can be caused by electronic noise or disturbances in the measurement path of the sensors. Spike detection is done by computing the mean and standard deviation for a series of 5-minute moving windows with a 2.5-minute overlap. Points which are above certain multiples of standard deviation is detected as a spike and is replaced with a linearly interpolated value. But if 4 or more consecutive points are detected, they are not counted as spikes. Data is hard flagged when the total number of replaced spikes exceed 1% of the total data points. Some of the common plausibility ranges used for despiking are presented in this table. Note that for methane and N2O, a large standard deviation range is prescribed as these gases are released in ecosystems as pulses or in episodic events. The second test is the test for suitable amplitude resolution. Insufficient amplitude resolution occurs in conditions of weak variance. The instrument resolution is not enough to capture all the fluctuations occurring in the data. An example of a true signal is shown in the first diagram as the red line, and the same signal sampled with a low amplitude resolution is shown in blue. This can also occur due to faulty instrument or error in data recording. Amplitude resolution flags are identified using a series of discrete frequency distributions which are created by binning the data into 100 bins in 1000 data point half overlapping windows. If the number of empty bins in each frequency distribution exceeds a critical threshold value, say 70% for 10 Hz data, the data is then hard flagged as having an amplitude resolution issue. Now let's see the third one, which is the hard flag for dropouts. Dropouts occurs when the time series sticks at a constant value, which may be due to an unresponsive instrument or an electronic recording problem. These kind of events may not be identified by despiking procedures. It is identified by using a similar methodology using discrete frequency distributions. Consecutive points which fall into the same bin of frequency distribution are identified as dropouts. When the total number of dropouts in any frequency distributions exceeds a critical value, say 10%, the averaging interval is hard flagged for dropouts. The absolute limit flag is discussed next. Unrealistic data can be recorded due to instrument error, recording errors, or due to obstructions in the sampling path. The presence of unrealistic value is used as a criteria to hard flag the data. Some of the typical physical limits used are present in this table. Now coming to the fifth one, which are the higher moment statistics. These are used to flag possible instrument or recording problems and physical but unusual behavior. Skewness and kurtosis of the time series is calculated to flag the data. Skewness is the degree of asymmetry from the normal distribution, and kurtosis is the peakness of the probability distribution. The data is detunted before computing higher moment statistics to remove potential contribution of trends. Skewness and kurtosis are then computed, and data is hard flag when the skewness is less than -2 or greater than 2, or if the kurtosis is less than 1 or greater than 8. I have provided an example of a higher moment statistics calculation for sonic temperature here. The skewness in this case is 0.17 and the kurtosis is 3.17, which indicates a good data quality in terms of higher moment statistics. The next two hard flags discussed are based on discontinuities and time lag between data streams. Discontinuities are sharp changes in data pattern and can occur due to environmental forcings or instrument errors. These are detected using a hard transform on the data in a series of moving windows. The hard transform calculates the difference in some quantity over two half-window means. This transformed value is normalized, and hard flags are applied if the absolute value of a normalized transform exceeds 2 in any window. The last hard flag discussed here is based on time lag between sensors. Presence of lags in data from two different sensors can be used as a criteria for flagging data. Physical lags can occur due to sensor placement, but systematic lags can indicate instrument problems. A lag correction ratio is calculated based on the maximum correlation in a predefined window and the absolute correlation at 0 lag. The window selected can change based on the type of the instrument and can be longer for closed path sensors based on the intake dimensions and the flow rate. A record is hard flagged when the lag correction ratio exceeds 0.1. In general, all hard flags are calculated on corrected data. Hard flag data has to be visually inspected to identify if there are any actual physical reasons for the unusual behavior. If so, the hard flags, you can convert them to soft flags. To recap, now we have covered some of the different kinds of hard flags. The next step is coordinate rotation. Wind streamlines and instrument coordinates are different due to uneven terrain or due to sensor tilt errors. So the coordinate rotation is intended to level the sonic anemometer to a reference surface and to bring all the estimated vectors to this new coordinate system. This can be achieved using two different methodologies. They are the two-dimensional rotation and the planar fit method. In the two-dimensional rotation, this involves getting the wind velocity components aligned to the natural coordinate system. So the natural coordinate system is a right-handed system in which the x-axis is parallel to the mean flow and the z-axis is normal to and pointed away from the underlying surface. The first rotation here is to get the wind velocity components measured by the instrument aligned to the mean wind direction. In other words, this is swinging the instrument x and y axis about its z-axis to the x and y axis of the natural coordinate system. This rotation will set the mean v velocity to 0. In the second step, the second rotation is to align the velocity components to the streamline of the terrain. This is swinging the new x and the original z-axis about the new y-axis. This sets the mean vertical velocity to 0. Now the instrument coordinate system is transformed into the natural wind coordinate. A third rotation can also be done, which forces the VW covariance term to be 0, which you can call as a three-dimensional rotation. This rotation has closure problems and often gives physically unrealistic values, and so it is not implemented in most cases. Now let's examine the planar fit method. In this method, a tilted plane or mean streamline plane is defined using average wind velocity data from a particular time period. This is accomplished through a polynomial regression. The average wind velocity components are used to develop this regression. This data is used when the instrument position was not changed and the length of the observation period has to be at least a week or longer. The unrotated velocity components are rotated into this new tilted plane in the planar fit method. Pitch, roll, and yaw angles or rotation matrices are described in terms of the regression coefficients. A partial rotation matrix P is defined that places the vertical axis perpendicular to the mean streamlines. The unrotated wind velocities can be multiplied with the P matrix and then rotated into the mean wind direction by multiplying by the M matrix. Now the wind velocity components are in the new plane.
James, I have a question from the audience. What are the major differences between 2D rotation and planar fit in terms of application?
Thanks, Ashley. That's a good question. 2D rotation works well in flat homogeneous terrain. It allows online computation of fluxes as calculations are not complicated, whereas planar fit is recommended for uneven terrain. And again, each method has its own advantages and disadvantages. In 2D rotation, over-rotation can occur, leading to bias in integrated carbon flux, loss of information about the true nature of the flow, and degradation of data quality can also occur. The planar fit method actually overcomes many of the disadvantages of the 2D rotation, but still it is difficult to quantify the mean streamline plane for heterogeneous terrain or for fast-growing crops. And even minute changes in the actual instrument setup can affect this rotation procedure. Okay, now let's get back into the presentation. So after the coordinate rotation, the next step is correcting sensor time lags. Time lags can occur due to electronic lags and orientation of sensors in relation to the prevailing wind direction. Unaccounting time lags between signals can lead to underestimation of fluxes. Although fixed time lags can be prescribed based on non-electronic delays in data processing, this will not take care of the lags caused by sensor separation, which exposes each instrument to a different flow regime. Lags can be corrected by calculating cross covariance or correlation between the data from two instruments and aligning the signal based on the lag at which maximum correlation or covariance is observed. Maximum and minimum time lag windows are to be specified, within which the maximum covariance or correlation is estimated. These time lag windows can be defined as functions of sensor separation for open path and as functions of flow rate, intake length, and diameter for closed path instruments. Nominal time lags are to be prescribed as under weak turbulent regimes. True peak correlation or covariance is difficult to estimate, in which case the nominal time lag is used to align the time series. So after correcting the time lags, the next step is detrending. Separating the mean and the fluctuating part of a time series is essential for estimating fluxes in the Eddy Covariance methodology. This can be achieved in three different ways: block averaging, linear detrending, and filtering. In block averaging, the mean is subtracted from each individual value of the time series to obtain the fluctuations. In linear detrending, the linear trend in the data is subtracted from the entire series to obtain the fluctuating part. In filtering, the time series filtered to establish the mean values. For example, use of a moving average filter. Block averaging is the most common methodology. However, linear detrending and filtering may be needed in complex terrain or in rapidly changing concentration regimes. Block averaging and linear detrending are not filtering operations, and their influence on signal spectra can be easily approximated by using transfer functions. Block averaging can gain some artificial flux, whereas linear detrending and filtering can lose some flux. So after detrending, we obtain the raw uncorrected covariance terms. The next step is correcting the WTV covariance for humidity effects. The first step in correcting the WTV covariance is to correct the sonic temperature for crosswind effects. Sonic temperature is estimated from the speed of the sound in air estimated through the transducer flight times. Speed of sound is underestimated in the presence of a crosswind, and a crosswind is the wind component normal to a velocity measurement axis. Since speed of sound is calculated along the three axes is used for sonic temperature estimation, the crosswind component in all three transducer axes have to be considered for correcting sonic temperature. The crosswind component can be calculated as a function of the velocity components and the angle of the orientation of the transducers. Hence, this term is estimated differently for different anemometers. This crosswind correction term is applied internally for many anemometers, and for a few it is not. So in that case, you have to apply the crosswind correction. For some anemometers, you can even turn it on and off. Sonic anemometers measure sonic temperature, which can be approximated or which is very similar to the virtual temperature, which accounts for the moisture in the air. To get the actual sensible heat flux, the moisture effects have to be removed. That's to convert the virtual heat flux to actual heat flux. This is accomplished by the first term given in the presented equation. The second term in the above equation is the crosswind correction term, accounting for the three-path averaging of sonic temperature on temperature variance and flux. The A and the B terms in the crosswind correction term depend upon the anemometer geometry. And again, if crosswind correction is internally applied, there is no need to apply this term in the flux calculations. An accidental application of this term can lead to overcorrection of fluxes. The corrected WTV covariance term is usually lower in magnitude than the uncorrected term. And so the next step is, once you have corrected the WTV covariance, is to apply the spectral corrections or the frequency response corrections. Frequency response corrections are a family of corrections which are applied to account for the inability of the instrument to have an ideal frequency response. The covariance data collected from an instrument or instruments with non-ideal frequency response will have an attenuated co-spectral shape. Co-spectra describes how much flux is transported in each frequency, and the integrated area under the co-spectra represents the flux. The total flux loss can be represented as a difference in area under the ideal and the estimated co-spectra. The graph shown here has three different co-spectral plots. The ideal co-spectra is shown in yellow, and the red and the green denote co-spectra obtained from non-ideal instruments. The X scale is increasing frequency, and you can see that the non-ideal co-spectra has lows both in the low and high frequency part of the spectrum. And a variety of reasons can be identified for the non-ideal frequency response of Eddy Covariance instrumentation. All of these are related to the system or to the instruments themselves. Some of the important factors are presented in the table. The inability of the sensor to respond to scalar fluctuations contributes to spectral attenuation. Sensor separation creates situations in which the sonic and the gas analyzers don't sample the same volume of air, which can also lead to spectral attenuation. The length and the volume of the sampling path restrict the size of the eddies that can be sensed by an instrument, leading to spectral attenuation. The smallest eddy which can be sensed by an anemometer has a size which is equal to the path length of the instrument. So attenuation of scalar signals can also occur when samples are drawn in through intakes, leading to spectral attenuation. Averaging operations and electronic filtering done inside the sensors can also cause loss of information in the high and low frequency part of the spectrum. Mismatch in sensor response, which arises when data from fast and slow instruments are used together, is also a contributing factor to spectral attenuation. Frequency response correction or spectral corrections can be implemented in three different ways. The first method is the numerical integration method proposed by Moore et al. In 1986. In this method, a model of unattenuated or true co-spectra is described. Then transfer functions are defined to represent the attenuation effects. The transfer functions are multiplied with the true co-spectra to obtain the attenuated co-spectra. The ratio of the two true integrated co-spectra to the integrated attenuated co-spectra is the correction factor, which, when multiplied with the attenuated flux, gives you the true flux. The second method, the analytical method proposed by Massman, provides an analytical solution to the integration method. This method has very few calculations involved and can be incorporated for online flux calculation. The third way is the passband method. In this method, the ratio of the true and attenuated cospectra is directly used to calculate a correction factor. The true cospectra is the region of the estimated spectra which is assumed to have no spectral attenuation. This method requires actual estimation of cospectra for every averaging interval, and so this can be numerically intensive. So in this presentation, I'm just going to cover in detail only the numerical integration method. The integration method proposed by Moore et al. Utilizes transfer functions to represent the attenuation effects. A transfer function provides a mathematical relationship in terms of spatial or temporal frequency between the input and output of a system. A true model cospectra is prescribed, and then it is multiplied by a combination of transfer functions to obtain the attenuated cospectra. Transfer functions can be constructed by describing a normalized frequency series. This can be done by describing a logarithmically spaced sequence from a very low frequency, say 10⁻⁻⁵, to the Nyquist frequency, again, which is half the sampling frequency. The transfer function for sensor time response is plotted here, which is calculated using the described frequency series and the dynamic time response of the sensor, which is 0.1 seconds. The transfer function for path and volume averaging is estimated using the sampling path length and the mean wind velocity. The transfer function for sensor separation is estimated using the separation distance between the two sensors and the mean wind velocity. Transfer functions for high-pass filtering and low-pass filtering effects use the filter coefficients, cutoff frequencies, and sampling frequency. The transfer functions for tube attenuation is estimated using a tube attenuation parameter, which depends on the nature of the gas involved, the tube diameter and length, and the mean tube flow velocity. For digital sampling, the attenuation parameter requires only the sampling frequency. The transfer functions representing a sensor response mismatch requires the dynamic time response of both the sensors involved. So after describing all the attenuating transfer functions, a total transfer function is defined. This is done by multiplying together the various transfer functions. Some of the transfer functions are squared as certain attenuating effects apply to both signals involved in the covariance, whereas the square root of some others are taken. This total transfer function is multiplied with the model true cospectra to obtain the attenuated cospectra. The ratio of the integrated attenuated cospectra to the true cospectra gives you the correction factor. This correction factor can be multiplied with an attenuated covariance to get the true covariance.
All right, here's another question from the audience. What is the influence of spectral correction methods in final fluxes?
That's another great question, actually. Let me try to answer this one. Frequency response correction can increase the flux in many cases from, say, 10 to 18%. Frequency response corrections for tube attenuation has the highest contribution among the different frequency correction terms. The reference true cospectra shapes prescribed by the different methods are different. The Keimer and the Moore cospectral shapes look similar, whereas Massman's true cospectra has a different shape. Hence, the amount of spectral corrections you get from the different methods can be different. Okay, now let's get back to the presentation. The next step is the WPL correction, which is described by Webb et al. In 1980. The WPL correction is considered more as a physical effect than as a correction, as density measurements are always influenced by water vapor temperature and pressure. The fundamental equations of Eddy covariance requires mixing ratio measurements, but most instruments measure density, which can change with temperature, pressure, and water vapor. Let's consider the case of a parking lot on a hot summer afternoon. Okay, the air which rises up from the surface will be warmer and will be expanded, and thus it will have a low CO2 density than air which is flowing downwards. Thus, the net effect will be a false downward flux without an actual CO2 sink. Similarly, in the case of a wet surface where there are no CO2 sinks, the air rising up from the surface will be moist and will have a low CO2 density due to the dilution effect of water vapor. And so compared to the drier, denser air which is flowing downwards, thus creating a net decrease in CO2 as air rises up, indicating a false sink for CO2. This expansion and dilution effect has to be deducted from the measured covariance to obtain a corrected flux. The complete form of the WPL corrected flux is presented here in terms of the dilution and the expansion terms. The temperature term has the highest contribution to the correction term, whereas the pressure term always contributes positively. The magnitude of the WP covariance term is very small and is important only under certain atmospheric conditions where you have low pressure and high wind velocities. The CO2 self-dilution effect and the higher order effects are also presented here. So WPL correction for closed path sensors is required when measurements are obtained as small fractions. The temperature expansion term can be neglected for closed path as sampling through long tubes can attenuate temperature fluctuations. Temperature attenuation in an enclosed erga like the LI-7200 is presented as a function of tube length here. And you can see that the most of the temperature fluctuations are attenuated by a tube length of about 1 meter. The dilution correction is only applied in this case actually, and the time lag synchronization used for scalar concentration should be used for water vapor also. In the case of temperature and pressure control systems, a temperature and pressure normalization with values within and outside the measurement cell is recommended. Now let's see the frequency response corrections, how they are applied to the various WPL terms. So in the case of an open path system, the attenuating corrections that represents the aggregated instrument and system related effects have to be applied to all individual covariance terms. So all the covariance terms are measured for variables in the atmosphere, and hence these corrections are needed to be applied to each covariance term. But in the case of closed path instruments, the frequency response correction is applied only to the scalar covariance in question and not to the dilution or the expansion terms. The WPL terms in this case arise from the environment in which the measurement is made, and that is inside the measurement cell, which is inside the instrument. As I mentioned before, utilizing the true mixing ratio in flux calculations avoids the needs for WPL correction. The LI-7200 enclosed gas analyzer facilitate point-by-point conversion of density measurements to mixing ratio, which is done by utilizing the fast temperature and pressure measurements, thus avoiding the need for the WPL correction. The identical fluxes obtained through the WPL correction and the fast mixing ratio calculations from the LI-7200 are presented in this graph here. In a recent publication, Nakai et al. Suggested that the minute differences you observe between fluxes calculated using the WPL correction term and the fast mixing ratio estimates in areas of low fluxes can be accounted to the lack of inclusion of the pressure term in WPL correction. After application of all the correction parameters, we end up with the final corrected fluxes. I have provided an example of the diurnal CO2 flux here. Photosynthetically active radiation and latent heat flux is also displayed. Latent heat flux shows a negative correlation with the CO2 flux, as the source of water vapor is the sink for CO2. That's the plans. CO2 assimilation increases with increasing light levels, and so does the latent heat flux.
James, I have another question. Do all these corrections apply to gases other than CO2, such as H2O?
Thanks, Ashley. That's a common question which comes up in Eddy Covariance data processing scenarios. Yes, the frequency response corrections and WPL corrections apply for water vapor, and other gases such as N2O and methane, if density of these gases are measured. As all density measurements suffer from dilution and expansion effects. But if true mixing ratios can be estimated by an instrument, it doesn't require the WPL correction. The frequency response corrections, on the other hand, is applied to all instruments. The frequency response correction can change for the gas depending upon the nature of the gas. Like for water vapor, which is sticky, you have a different frequency response correction than for CO2. And there may be additional correction terms like spectroscopic corrections for laser instruments. Okay, now let's get back. So after correcting the final fluxes, we need to determine whether the fluxes we estimated have the right or the required quality. This can be described using quality flags. The quality flags are developed based on whether the theoretical requirement of the EC measurements are met. This can be done by checking whether we have steady state conditions and a well-developed turbulence. Steady state condition means that all statistical parameters do not vary in time. Lack of stationarity can be caused by changes in meteorological variables with the time of the day, change of weather patterns, and also due to mesoscale variability. Stationarity in the time series can be determined through the following procedure. Time series for the determination of covariance is divided into 6 equal parts. Covariance is estimated for each section, and the difference between the ensemble average of the covariance for each section and the covariance of the entire series is expressed as a percentage to obtain a stationarity parameter. Flux variance similarity is used to test development of turbulent conditions. Integral turbulence characteristics are basic similarity characteristics of the atmosphere. The percentage difference between ITC measured and ITC model can be used as a criteria for developed turbulent conditions. So using a combination of ITC and stationarity criteria, various quality flags were developed. So one such example shown here is the overall quality flags developed after the Spoleto Agreement for Cabo Europe. The highest quality data, which is flagged as 0, is used in fundamental research. This category has ITC and stationarity parameter values which are less than or equal to 30%. The moderate quality data, which is flagged as 1, can be used for long-term observation programs. This category has ITC and stationarity parameter which are greater than 30%. The low quality data needs gap filling and is the worst quality, and it is flagged as 2. The ITC and stationarity parameter value is greater than 100% for this category. An example of quality flag sensible heat flux series is presented here, and you can see that most low quality data is observed during night hours when turbulence is weak. And again, to wrap up, in this presentation we have covered the fundamental theory of Eddy covariance data processing, the various corrections involved, and the methods to quantify the quality of the data. And again, most of these steps involved are complex and require really complicated calculations. And I've tried to go through most of these equations, but again, if you have software available which will do it all for you, you don't have to worry about this. Here are a few additional educational resources. Again, we have a full staff of scientists and individuals to help you answer questions, both scientific in nature or those focused on technical issues. And if you haven't seen our new Eddy Covariance web pages, there is a lot of additional educational information and resources there, including the Eddy Covariance guidebook, scientific posters, papers, and software. And now we have a new data processing software called Eddy Pro. This is available on our website for free download. An advanced version is being developed which gives more outputs and user selectable options for flux processing. We do offer a Eddy Covariance training. We have this 3-day classes available at LI-COR taught by our scientists. The course covers theory, design and implementation, hands-on installation of instruments, and proper techniques. We also spend a day on data processing corrections and data quality and assurance. We walk you through several experimental examples using Eddy Pro software and work together with you on a hands-on step-by-step instruction procedure. And here we take the raw data and convert it to publishable flux values. And you can register for these courses at the Eddy Covariance web pages. So this concludes the webinar, and thank you all for patiently attending this webinar.
All right, thank you for your presentation, James and Jia Hong. We don't really have any questions for a final Q&A, but if by chance something crosses your mind, our panelists will stick around to give you an answer, so you do have a few moments to submit some more questions if they cross your mind. If you haven't gotten an answer to your question yet, our panelists are still working on the questions you've already submitted. And if you'd like to continue your conversation with the panelist, you may do so offline via email or phone. Just grab that information from the panelist you've been speaking with. And I'd also like to remind you that the replay of this presentation will be posted to our website soon, so watch your email or visit www.licor.com/env/webinars for more information. And you can also watch the previous sections of this series there. So thank you for joining us today, and let us know how we did. We really appreciate your comments and suggestions, and we hope to see you at our next webinar.